Okay then, so we'll continue with our example on the logical effort now. So in the example here, we have a three-stage path going from node A to node B, and we want to find the optimum size for gate X and gate Y from A to B. And we already know the optimum size for, or we know the size for A for the first two-input NAND. Okay, and the size is 8. Okay, so the size in the beginning is given 8, and the output gate here is driving a 45. This is a relative capacitance or size. It's driving a 45 value on the output. So what is the optimum size for X and Y given the size 8 and 45? So first we need to find the path logical effort. So what is the logical effort on the path from A to B? Okay. So one thing to note here is when doing logical effort is considering the path. So in order to find the optimum size for every gate, you consider all the possible paths in the circuit. Okay. But in this case, mainly using the same gate, so the sizes can be the same. So here, what is the logical effort? So we have the small g here for a two-input NAND. If you remember, it's 4/3, and for a three-input NAND, our g is 5/3, and a two-input NOR, our g is 5/3. Okay, so then our g here is actually the product of the small g for all I. Okay. So 4/3 times 5/3 times 5/3, we have 100/27. That's our path logical effort. Our electrical effort, H is simply 45 divided by 8. Okay. So previously in the inverter, this electrical effort is called the effective fan out, overall effective fan out. But here is simply the H, or the electrical effort. The branching effort is 3 times 2 times 1. So how do we get there? So here we have a fan out of 3. Okay. So this B here equals to 3. Let's say B1, and then our B2 is 2. B2 equals to 2, and here is our B3 equals to 1. Okay. So in the end, we have our total here is I for BI. There's a product of individual branching fan out, so 3 times 2 times 1, and therefore our capital F is simply GBH. Okay. So this guy times this guy times this guy. Okay. GBH equals to 125, and then to get the small f, the best stage effort is to see how many gates do we have, or how many stages we have in the path, in the flow. So we have 3 gates. So we find the third root. Root of 3 of f is equals to 5, and therefore our delay is simply 22 TP0. So here is your P. Okay. So your P here is 2. Your P here is 3, and here is P equals to 2. So your total parasitic is 2 plus 3 plus 2. So this is your P, and here is your small f. Okay, and we have 3 gates there, so the total is 22 TP0. Okay, so how do we get the size? Just now we just analyzed the total. We know the total delay, we know the small f. So how do we get the size? So similar to the inverter method that we did. So we can find the size C in is C out, C in I equals C out I times GI over F. So in order to get the size Y, is just 45 times 5/3 divided by 5. Okay, so here is actually CL times GI over FI. Okay, or the F. We don't need the I. Okay, so CL GI over F. Okay, equals to, because our F is CL over C in times G. Okay, so here is actually your HG. Okay, so F is HG. F is HG and H is CL over C in, and therefore we can solve for C in, which is CL over F times G. Okay, so what about X? So for X, so for X here we know this is 15. Okay, this is 15, and we have a branch of 2, so we have 15 times 2. Okay, so this is your C out. Okay, C out times 2 times the this is your G. Okay, your logical effort for this guy, divided by 5, which is your F. So here's your F. Okay, so C out G over F, and we get a 10. Okay, and just to validate the capacitance at the input, we can validate. If this is 10, 10, 10, so here is 30. Okay, and G here is 4 over 3, and then we have F here is equals to 5. So 10. So this is your C out. Okay, this is your G, and this is your F. Okay, so if you do the calculation correctly, you should be able to get validate that your input capacitance or your input size actually match to our analysis. And if you get the wrong number, if you don't get 8 here, okay, then something is wrong with the calculation. Okay then, so let's continue with this. So we obtained the size already, the optimum size for each one. So in the initial one, we already found, it's already given to you. The size equals to 8 here. So the size here is equals to 8, and then for the second one, the size, we have a size equals to 10, and here we have size 15. So given the relative sizes, the optimum relative sizes that we have computed, how do you obtain the size of the individual transistors? So here, for example, size 8, this is the input. Okay, so this is the C intrinsic of the logic gate. So the intrinsic is simply the gate size. You can say the relative gate sizes. So as we've seen in the previous slides, in the previous video, is essentially is the total size of relative capacitance at the gate input of A. Okay, at the gate input here. So if you imagine at the gate input there, we have one NMOS. A is connected to one NMOS and one PMOS. And if we set the size 4 and 4, we're going to get a total gate size of 8, which is proportional to the capacitance at the gate. So a size 8, and we want to achieve a certain ratio of beta. So here, for example, we have a beta of, let's see, for a 2 input, this is a beta of 2. Okay, so P equals to 4, N equals to 4, we can calculate, and we can prove that actually it's a 2-to-1 ratio of the effective PMOS and the effective NMOS. So here for a 3 input, we make a size of 4 and 6. Also, I believe should be beta 2, and here is also beta 2 for a size 15. So for a size 15, we have. Okay, let's look at another example here. So we have a quite small and simple circuit here. It's a four-stage logic, inverter, NAND gate, NOR gate, inverter. So for this network, we want to find the size, the best optimum size for gates A, B, and C. So first step is we need to find the F. Okay, and F is equals to GHB. F equals to GHB, and let's look at H first. So H is equals to 5. How do you get 5? So H is the electrical effort. Is quite straightforward, 5 over 1. Next, let's look at branching first. Okay, the b equals to 1. So if we consider from A to B, let's say here from A to B, and we take the line from A to B, we are going to go through this particular path, and we see that there is no branching. Okay, there is no branching from A to B, and therefore we have b equals to 1. And what about G? So G is the product of the logical effort, and the logical effort here is G equals to 1. Here is G equals to 5 over 3, G equals to 5 over 3, and G equals to 1. And if you take the product of the individual G's, you are going to get the overall logical effort. So in the end, if you multiply BGH all together, you get 125 over 9. So then you get the F is the root 4 of F, where you get your 1.93. Okay. So your small f is 1.93, and from this you can already calculate or estimate your propagation delay, because we know the f for each one. Okay, so 1 plus GH times TP0 for each gate. So what was the finite factors? So here they calculate the finite factors. So H so here H is actually equals to F over G. Okay, F equals to GH. So F we got, so 1.93, we got it from here. And then our G is for inverter is equals to 1. Okay, and for gate A, H here is the F is fixed, 1.93, and here is 5 over 3. Okay, so we have HA is 1.93 times 3 over 5, and for B is the same. For B is also the same, 1.93 over 5 over 3, and C is just 1.93. Okay. So what is the gate size? So H here is actually equals to F over G, but H is also equals to C extrinsic over C intrinsic. Okay, extrinsic with intrinsic. So once we calculated the H, if we have H and we have the C extrinsic, we can then find the C intrinsic. Okay, so for example here, the C intrinsic is actually simply equals to C extrinsic divided by H. Okay. Okay, C intrinsic is C extrinsic divided by H. So H we obtained already. So we work backwards. So what is the size for C? So size for C, for example, C int for C, okay, is equals to CL over H equals to 5 over the H is H for C is 1.93. Okay, then we should get equals to 2.6. Okay, 2.6x. Okay, so we know now that the size of C is 2.6, 5 over 2. Okay, so C should be made 2.6 bigger than the first inverter, because the first inverter is size 1. Okay, so here is size 1, here is going to be size 2.6. Okay, and if you do the same, for the others, you're going to get 1.34 at gate B, 1.34, and then we're going to have 1.16 at A. Okay, 1.16 at A. 1.16 at A. Okay, let's look at the last example here. Our first, if you remember our first page, our first slide, this Mr. Ben Diddle, the memory designer from Motorola. So he wants to know how to best design the 416 decoder. Okay, how many stage to use? What is the logic here? How many stage to use? How large should each gate be? And how fast can we operate the decoder? Okay, so here is a partial block diagram of the gate level implementation of the decoder. And basically your address is here. So you have the A0 and A0 bar, the complementary of the address. Okay, so 4-bit A and 4-bit A bar, and then the output is here. Okay, and the output is the output is connected to this is an inverter and a 4 input. So it's a NAND 4, and then we have an inverter here and an inverter here. So basically, one possible implementation. There are few other implementation as well. We'll see in the next slide. But one possible implementation is to have a 3-stage logic where it goes through one inverter, one NAND gate, and one another inverter at the end. Okay, another inverter at the end. Okay, so what is the path logical effort? So we are looking at, for example, one line. So let's take this line. So if we take this line, okay, and it's connected to here is connected to another so this is 16. So we have 16. So it's connected to 7 more NAND. Okay, so here is down is yeah, it's connected to 7 more. Okay, so this is the first one. Okay, and then you have second one until 7. So in total you have 8 fan out. Okay, so here you can say you get 8 fan out. Okay, so the output of inverter A0 is actually connected to 8 other 4 input NAND gates. Okay, so in that case, our branching effort, okay, our branching effort is 8. Okay, because this is 1, so only in the middle of there. So our branching effort is 8. And what about our H? So this is your P. Okay, this is your G and this is your H. Okay, what about our G? So our G is just this is 1, this is 1, and this is 2. So a 4 input NAND gate, your G is equals to 2. Okay, your G here is 1, your G equals to 1. So in total your G is 2 times 1 times 1. So you have a G equals to 2. This guy, and your H is 96. So here at the end here you have 96. Okay, so here is actually connected to 96, and then your input is 10. Okay, so 96 divided by 10, we have 9.6, and if you do the multiplication, you get 154. And how many stage we have? We have 3 stage. So f to the root of 3, we have f equals to 5.4, and from there we can find the path delay, which is the parasitic inverter NAND gate inverter 3 times f, 22.1 TP0. Okay, and what is the gate size? The gate size you can find using this equation. So 96 times 1 over 5.4 equals to 18, and then for y, 18 times 2 over 5.4, you get 6.7. Okay, so those are the gate sizes that optimize the delay using 3-stage logic. Okay, the 3-stage logic for the decoder design. Okay, so we have this total delay. That's our goal. We want to have a fast circuit. So is that the best we can do? 22.1 TP0, or maybe we can use a 1-stage logic, or maybe more, maybe 4-stage logic, different kind of logic, and we can then calculate the delay. So here they made some comparison. The one that they did here is this one, 22.1. So 22.1 is there using 3-stage logic. Your total G and your total P given there. Okay, but in fact, if you do a 1 stage, okay, n equals to 1, you have a very large TP0. So the optimum one, we can probably estimate using some equation, but here I think we're not going to do that. So basically you can just make some experiments yourself to test different logic styles, different logic circuits stages, okay, and the best one can be found here, in fact, using n equals to 4. Okay, so n equals to 4, we have our G is 16/9, our parasitic equals to 6, and our total delay is 19.7 dp0. Okay, slightly better, slightly better than the 3-stage design. Okay, so here's a summary of the definitions. I think you can see this for yourself, and finally, let's look at some of the limits of logical effort. Is it perfect? It's not really perfect, but it is a good starting point, a good estimation to think in terms of delay. But here it's mentioned it's a chicken and egg problem. Okay, which one comes first? Because in order to compute G, which is the total logical effort on the path, you need the stages, right? You need to know what gates are in the stage, but we don't know the number of stages without knowing G. So it's a chicken and egg problem there. It's quite simplistic. It neglects the input rise time effects. Okay, it's a quite simplistic delay model. The interconnect, the iteration required in designs with wire, maximize speed only, so not minimum area power for constraint or delay. So here's the issue here, is that the logical effort is trying to optimize the speed, and if speed is our main criteria, our main objective, then okay, we might be able to achieve it. But nowadays people talk about area and power, and if you make your design big, which is the case, if you need to be fast, you need to make your inverters or logic gates a certain size, and it might be big. So it's going to impact your area and power. It's going to cost more, and it's going to drain battery faster. So there is something to consider when using the logical effort methodology. So in summary, the logical effort is useful for thinking of delay in circuits. The numerical logical effort characterizes gates. NANDs are faster than NORs in CMOS. It's quite interesting to see. NANDs are faster. Okay, so preferably we want to use a NAND gate instead of a NOR gate. Paths are fastest when effort delays are around 4. Path delay is weakly sensitive to stages and sizes. Using fewer stages doesn't mean faster path. Okay, this is another interesting part here. So normally, if you think as a digital designer might think that to make it fast, you need less logic gates, right? Less logic gates, less number of stages in your line, in your path, then you'll be faster. But that's not necessarily the case. Sometimes you need more stages to be faster in the line or in the path. Inverters and NAND are best for driving large caps. Okay, so if you're driving a large output, a large fan out, then you want to use inverters and 2 input NANDs for it. Okay, so provides language for discussing fast circuits, requires practice to master. Okay, so we're done with the logical effort chapters, and we have one more topic to go for this semester, which is on power analysis, which we'll cover in the next video.